We're now going to apply the tools that we looked at last week in the introductory concepts to actually working with real estate examples and some more elaborate models for property investment valuation or investment property valuation. The exercise we're going to run through today or now are self-correcting. That means that they've been designed to be able to do it yourself, because when you enter the correct equation, sometimes the correct number, but usually equation, the yellow highlight will disappear to tell you that you've got the right answer. If you put the equations in correctly and get rid of the yellow highlight, not only have you solved the problem that presents you in the exercise, but it means that you're actually building your own model, and these are becoming a useful set of Excel models, if you like, that you can use for serious, proper calculations. And so you can change the data, which is in blue, and as long as you've got those yellow highlights going around, so your mathematics is good, you can apply it to other properties, maybe real properties. You may have an investment property of your own that you may like to run these things through. And so while sometimes getting rid of those yellow highlights can be a little bit frustrating if something's going wrong or what have you, know that the answer and the time you spend with it is worthwhile. Remember to check your calculations with that squared paper and your financial calculator side by side. It helps your learning. It helps you develop those skills so that you can use your financial calculator like you ride a bicycle. And it also gives you a little bit of proof, if you like, that the Excel models are also working. Beware, on occasions, the yellow highlighting can be a bit oversensitive to rounding errors. And so there are rare occasions with these more advanced models, not necessarily what we're going to be doing in this module, but further on in the unit, where you may find the yellow highlights don't disappear, and it might be because of some kind of rounding or something that you've put in. Most of the time it's because of an error. Sometimes it can be due to rounding. I think I have most of them taken out now so that the precision is adequate, but there still might be one or two little gremlins hiding in there. They seem to come up mysteriously even when you think that they're all gone. However, I think for probably 99.9% of the exercises you'll find that the self-correcting will work happily for you, especially if you use the blank models as you get from Moodle and follow what I'm doing as we work through the videos. You shouldn't have any problems, and so it should work quite famously for you. If you do find that the yellow highlight persistently doesn't go away and you're quite sure that you're correct, send me an email, let me know, send me a copy of your file. Don't send me a screenshot. Those things are nice to look at, but they don't really help get to the mathematics which is lurking behind the numbers. So send me your model, tell me where the wheels have fallen off or what have you, and I'll be keen to have a look at it for you. And that'll help not just you, but also future students. Okay, let's get into these models now. When you open this exercise, be sure to read through the introduction sheet. This is the very first tab. It may not necessarily open with the introduction sheet when you open the Excel file. I'll let you read that in your own time. The first sheet that I want you to look at closely is what's called the financial functions diagram. This introduces the concept of a cash flow diagram. I recommend strongly that you consider drawing up cash flow diagrams when you have practical problems to be solved. There's a lot more on this sheet than the actual diagram, by the way, and so what you need to be able to draw up is actually quite simple. In fact, all it is a timeline. Here the timeline runs from time 0, which is today, out to about 10 or 12 years, and I'm really interested in the first 10 years on this diagram. A cash flow diagram is really nothing more than a timeline with the respective cash flows shown, where the cash flows that are going out of my pocket, that is payments, are down arrows, and the cash flows that are coming into my pocket, or cash receipts, are up arrows. In this case we can see that there is a receipt happening at the end of the first year of $100. There's another receipt of the same amount happening at the end of year 2, and so on, years 3, 4, and so on up to year 10. In year 10 it's considered that there is a notional sale, that the property in this case might be sold, and the value here we have is $1,000. Obviously that's a very inexpensive property, it might be $1,000 or something, but for our purposes it gives us an idea of what's going on. By the time we take all of these cash flows, the rental cash flows happening year by year, plus the notional sale at the end of the period, that really gives us the total value of the property to us. And what we have to do is work out its present value. If you're drawing cash flow diagrams to help you understand some particular problem, all you really need to do is draw the timeline and the indicative up and down arrows with some indication of about what they are, or at least where the important ones are. You'll find that by doing this it makes it a lot easier to conceptualize often very complex cash flow situations. While I'm only showing one row of receipts in here, you may want to split that up, say as rent on the land or ground rent split out from the total property rent or something. So there's a lot of flexibility with how you use this thing. It does help us though to conceptualize what happens through the discounted cash flow process. In this example we can see that we're using a discount rate of 20%, and what that means is that the $100 that I'm going to receive in 12 months time is discounted by 20% over 1 year, which means that the $100 is discounted by a factor of 0.8333, and calculating this we have come across before, and that leaves the $100 really only being worth $83 today. Similarly with the receipt in year 2, the $100 is really only worth $69.44. These calculations down here, by the way, are not strictly speaking part of the cash flow diagram. They're the computations that I'll eventually make. I'm putting them in here for purposes of illustration. But when you draw a cash flow diagram, what I'm wanting you to think about is the logic of how the cash flows into the future either roll up back to the present as a single present value amount, or perhaps in some cases how they may be using the discount factor moved into the future, so that they all end up with what their notional future value is by the time they've been compounded at the discount rate. We can see here that at 20%, $100 per year of rent plus a notional sale of $1,000 is only worth $580 today. We can see what happens as the discount rate changes. I'm going to take this discount rate and take it down to 15%. What you'll notice there is that the $500 and something has now increased up to $749. That's nice. If I take the discount rate down to 10%, the PV, the value of the property, is again increased, this time to $1,000. If I take it all the way down to 0, then the PV, the present value of the future benefits of owning the property, which is the rents plus the notional sale, is now up to $2,000, which is about as high as it can get, and those with a bit of quick mental arithmetic will notice that $2,000 is nothing more than the sum of 10 times 100 plus 1,000. So that's your cash flow diagram. Rather than doing these things year by year, as we saw last week, we can use the Excel functions, and down here in this panel is an example of the different Excel functions that are particularly relevant to this system or this situation of calculations. We introduced the Excel PV function last week. And here it is illustrated across here to give the 2000, and you'll notice that the discount rate is 0%. Let's bring the discount rate up to 15% to make it a bit interesting. And here we find it calculating the present value, or the value of the property, as $749, which you can see worked out here longhand. Okay, that's probably as much as we need to do by way of introducing the cash flow diagrams, except that I once more recommend to you to consider doing these when you have real problems to work out, especially things in partial value or refurbishment problems, or things like working out ground rents. Drawing up at least the blue part, this blue line with the up arrows and the down arrows, can be very, very handy way of getting the concept of what's going on actually sort of down on paper. Let's move now to the actual calculation exercises. In this first exercise, we're going to use the Excel financial functions, but from the point of view of loan calculations. These are useful to be comfortable with, but also they give you good practice in applying them in real-world situations. And property finance is certainly one of the issues that you'll have to deal with from time to time in your modelling. Let's look now at how we model a simple mortgage loan. Let's work down what has to be calculated. The first thing we have to do is work out the total number of payments. These are the total monthly payments. To do that, we're going to insert an equation which is equals 25, or the number of years, multiplied by 12, which is the number of months in a year, and it gives me 300. And by entering 300, the yellow highlight disappears, telling me that I have the correct answer. Likewise, the monthly interest rate. Here the monthly interest rate is simply going to be the annual interest rate divided by 12 months. Now this is the simple nominal monthly interest rate, and I use nominal interest rates because that's what banks use when they're working out loan calculations. It actually makes the banks a little tiny bit more money than if they were to use effective interest rates, but most borrowers don't notice and the banks are quite happy. Let's look now at working out the monthly repayment. To do that, I'm going to use the Excel PMT function. That's PMT, open brackets. Now we're going to enter the rate, which is the 1% that we've calculated per month, comma, the number of periods, which is 300 months, comma, and we're going to put a negative in to correct the sign conventions in Excel. We're going to put the present value, which for the loan is the amount that we borrow, and here I don't need to put any more parameters in, so I'll close the brackets, and that gives me a monthly repayment of $3,686, and so on. I can work out the total repayment by simply multiplying the monthly repayment times the number of months, which gives me an amount a bit over $1 million. To work out the total amount of interest that I've paid is done a little bit indirectly, but it's simply done by subtracting from the total repayments the actual amount that's being paid off the loan, which is the loan principal of $350,000. And so with that 25-year loan, I've repaid about $1.1 million. $750,000 has been in interest, and $350,000 is the actual repayment. So that is, we're paying back roughly about 2 times the actual principal in interest, or 1/3 of my repayments actually turns up as repaying the loan itself. The next thing I want to show you is how to calculate how much is outstanding at any particular time through the loan. Now this is a tiny bit tricky, but once you learn how it's done, you'll find it very easy to apply in other cases. So I'm only going to do it once here. I'm going to let you do the rest of the calculations yourself. The way you work out the principal sum part into loan is to work out what the PV is of the remaining cash flows. So I'll show you how that's done. Equals the present value of, now I'm going to use the rate of 1%. Here I'm going to say the number of periods is equal to 300 minus 5 years of repayment. 5 times 12, comma, put the negative sign to get my sign convention corrected, and my monthly repayment. And so what I'm saying is that to work out the principal outstanding, how much I still owe on the loan after 5 years of repayment, is done by, in this case, calculating the present value of 20 years of repayments. Let's see what that works out to be. So what that tells me is that in the first 5 years I've paid back, oh, what's that, about a bit more than $15,000. I'll let you correct out the yellow highlights here for the 10 and 15 in your own time. Likewise, to come down here and work out how much principal I've paid, I again do that with a simple subtraction. I say I started off with a loan of $350,000. I have now an outstanding principal of 334, and so that means I only have paid $15,000, despite having paid many times that in loan repayment. I'm going to leave you to calculate the remaining options for the 10 and 15 years. I want to move now down to the accelerated repayments. In the question, you'll notice that the situation is calling for analysis of what happens if I repay the loan a little bit faster. And so the amount faster is going to very simply be equal to the basic repayment multiplied by the factor of increase, which is going to be 1 plus the 10%. If I'd simply put in here the original repayment times 1.1, I'd still get the same answer. However, if someone was to change the 10% to 20% or 50% or something, my equation would not work. And so by always putting in the cell addresses when I have data implicitly being referred to, it makes sure that my model works for all cases. To work out how long the loan is going to take to pay off under this new higher repayment, I'm going to use the Excel function of NPER. Let's do that. NPER, open brackets, and it's a function that looks fairly similar to the PV function, except that you'll find, looking closely, the parameters are a little bit different. I'm still going to have the rate. In this case, I'm going to have the payment. I'm going to put a negative sign in there to say that it's a negative amount of money. The PV is still the $350,000, and with that I should be able to close that out. And that tells me that instead of the 300 months previously required, I only need 100 and, well, close enough to 200 months. So I've saved about 1/3 of the length of the loan by taking this higher repayment. If I work that out in terms of years, it's simply going to be that divided by 12. The total repayment here is going to equal the number of repayments, and I'm going to work this out exactly, even though I won't actually be working out a 0.12 payment. I'll be simply making a balloon payment at the end. It's going to be the total repayment is the number of repayments multiplied by the repayment amount. That's going to mean that my repayment now has come down from 1.1 million down to only 810,000. In other words, I've saved, well, I can work that out. I've gone from 1.1, now I'm only paying 810,000. And what we see is that there's something like almost $300,000 saved. You'll notice that that is all in terms of saved interest, because we're simply paying back the full principal in both cases. And I'll leave you to work out the progressive repayments at different periods through the loan. You will notice, however, that the major improvement tends to be in the earlier parts of the loan, but I'll leave that for you to discover. Let's move now to the next exercise. This exercise should be familiar from the previous module. All it is is the calculation here on Excel on a page of the compound discount rate that we introduced in Module 1 under the treatment of growth. Here what's required is to write an Excel equation which basically encompasses this equation. I think this should be fairly straightforward since you've already done this exercise, so I'm not going to do the demonstration of it, except that I expect you to be able to take this yellow highlighting out by writing the correct equation here. We'll move now to using compound discount rates. This is an application of the compound discount rate found in the previous exercise. Let's put this together. Equals, open brackets. Now our equation is very simply 1 plus the discount rate, close brackets, divide, open brackets, 1 plus the growth factor, close brackets, subtract 1, equals 11.22%. We're now going to use this compounded discount rate to solve this particular problem. And the problem is to work out the value to the landowner of this lease agreement, which starts off with a $100,000 rent. It's going to operate over 10 years. There's anticipated growth of 2.5% and a discount rate to the landowner of 14%. To do this, we can simply use the PV function, equals PV, open brackets. The rate now is the compound discount rate, number of periods. Well, we'll only calculate on a yearly basis, but that'll be satisfactory for our purposes. The payment is going to be the rent. We'll put in a negative sign to correct our sign convention, close brackets, and we have a term value of 583,000. That's the exercise. It is useful for you to see this calculation done longhand to kind of prove in your own mind that in fact this discounted cash flow equation, the term value of the lease to the owner, is in fact true. We're going to do that by doing it on the year by year basis. To work out the rent at the end of the first year, I'm going to put in my growth functions and I'm going to use absolute addressing. So my rent at the end of year 1 is going to be the present value of the rent multiplied by, open brackets, 1 plus the growth factor. I'm going to take that as absolute, and I'm also going to absolute the starting rent. I'm going to close my brackets, raise that to the power which is equal to the year number. That gives me $102,000. The present value of that is going to equal the future value divided by 1 plus the discount rate, absolute, close brackets, raised to the year number. And so that means that at the end of the first year I receive $102,000. That's only worth $89,900 to me in present value terms. To work out all of the rest of these, I'm not going to do all of the equations, I'm simply going to fill the equations down, nice little shorthand. I would say that you'll notice here the $72,000 still has a yellow highlight sitting on it. That will be a rounding error in the auto correcting system, so you can ignore that. To work out the net present value, the total value of the lease, normally I'd use the auto sum function, but since this spreadsheet is locked, I'll have to write it in longhand. Equals sum, open brackets, the correct answer, and you'll notice that the 583,000 is the same as what was calculated previously in one step. Obviously, this approach year by year takes a lot more computing than simply doing it in a single step. We'll move now to the fourth and final exercise, which are exercises in future value calculations.
We don't tend to use these terribly much, but it's important for you to have a little bit of experience and familiarity with them, because on some occasions they can be very, very useful, usually as a part of other models. This exercise is going to get us to calculate the value of funds which are being invested for a particular time to see how much money will be left at the end of the period. This is fairly straightforward. I can calculate these using simple discounting and compounding factors, but I'm going to use the Excel functions for demonstration purposes. So the future value of the present funds, that's the $10,000, can be worked out by using the FV function in Excel. Here I have the rate, I have the number of periods, I have no payments, I'm going to put in an extra comma, and then I'll put a negative sign for my sign conventions, the $10,000, and hit return, and I've got $20,000. So in 6 years time, earning 12.5%, 12.34%, the $10,000 becomes $20,000. Moving on to the regular payments, same function, equals FV, open brackets, the rate, comma, the number of periods, comma. Here we're going to use a payment negative, and I can just close out the function, and that gives me 8,185. The sum of the above, I'll use the auto sum function just for pure laziness. That gives me that sum. Now I'm going to check this by doing it all at once with the Excel FV function, and so save myself a little bit of time. The rate 12.5, the number of periods 6, the number of periods is minus that cell, and the FV is minus that cell, close brackets, done. And we can see that these are the same, and while you might say, well, I've got a test here, I'm giving you the opportunity to also test them longhand in the way we did with the previous exercise. I'm not going to bother to do that. It's going to be fairly straightforward for you, I think, to be able to work through and take out those yellow highlights. That completes these exercises. Make sure you do these yourself with the self-correcting exercise, so that you're not simply watching me, because it's important that you're able to use these functions quite flexibly and creatively as you build your own models. It would be even better now for you to perhaps use a blank Excel spreadsheet and do some of your own calculations totally yourself. And you can start with a cash flow diagram with the up and down arrows for things like loans or investments or rents or what have you, juggling them around the way you have with these exercises. The more conversant you are with these functions, the easier it's going to be for you to be able to interpret real live property problems into financial models into the future, which is exactly what this course is about.